Let's take a look at problem number 18. Find the absolute maximum minimum values of this function f of xy in the given region, x squared plus y squared is less than or equal to 36. So this is a crossover problem. It is connecting together ideas from 14.6 and 14.7. Let me explain why that is. So x squared plus y squared is less than or equal to 36. So that is a filled-in circle of radius 6. So our function that we're trying to optimize here, f of xy, it's a continuous function. And we know from section 14.7 that continuous functions attain both a min and a max on closed bounded domains. So we know that we are going to be able to find min and max. Not only that, but we know that the only place we have to look are two places. Number one, critical points on the interior of the region, and number two, on the boundary. So what we're going to do is that we're going to use 14.7 methods to find critical points that fall in the interior of the region, and then we're going to use Lagrange multipliers to optimize on the boundary. So crossover 14.7 to find critical points, 14.8 Lagrange multipliers to do the boundary. So let's go ahead and do that. To find critical points, we know we have to take the partial derivatives and set them equal to 0. So 2x minus 6 is equal to 0. 2y minus 8 is equal to 0. So x is 3, y is 4. And so our critical point is 3, 4. So let's just check to make sure this is in fact inside the region, inside the domain. 3 squared plus 4 squared is equal to 25, which is less than or equal to 36. So yes, 3, 4 is in fact inside our domain. It's possible that our critical point would fall outside the region, in which case we'd simply ignore it. Okay, so we know what's going on the interior. Now let's look at what's happening on the boundary. And to look at what's happening on the boundary, well, what should we do? We're going to use Lagrange multipliers. So we're going to min and max f of xy subject to g of xy is exactly equal to 36. Lagrange equations, gradient f is equal to lambda times the gradient of g. And so the gradient f, we've already calculated the partial derivatives here, so we can just list them off. 2x minus 6 and 2y minus 8. And that needs to equal lambda times the gradient of g, which is 2x and 2y. Okay, so we've done this part. Let me go to a new slide here so we can do the rest of the calculation. So let's recopy the Lagrange equations. 2x minus 6 is equal to lambda times 2x. And 2y minus 8 is equal to lambda times 2y. As we quite often do in these problems, let's try to make these expressions look like each other. So we multiply this by y and this by x. They are going to be the same right sides. Of course, we have to do the same thing to the left here. And so this is equal to this, and these two are the same, and this is equal to this, so these two expressions equal. So y times this, 2xy minus 6y, is equal to x times this, 2xy minus 8x. We see that we can do some canceling out. 6y is equal to 8x, or y is equal to 4/3 x. Okay, so at this point now, we've got y is equal to 4/3 x, and we're going to use our constraint that x squared plus y squared is exactly equal to 36. So let's use that now. X squared plus y is 4/3 x squared, and this is equal to 36. So x squared plus 16 nines x squared is 25 nines x squared, and that's equal to 36. X squared is equal to 9 over 25 times 36. So x is equal to the plus or minus the square root of that, and the square root of that is 18/5. So we've got 2 points that occur here, 2 points to think about. X is 18/5 and x is minus 18/5. And y is 4/3 times x. So 4/3 times 18/5 gives us 24/5. 4/3 times minus 18/5 gives us minus 24/5. So we've got these 2 critical points. These are the only places to look on the boundary. So now all we have to do to finish off the problem is to check our objective function, this f of xy, at these 3 points, and pick the biggest and the smallest values. So we'll look at the 2 points, objective function value evaluated at those points on the boundary and the one in the middle. And if you do these calculations out, I pre-computed these with a computer to make sure I didn't make any arithmetic mistakes. So that's just a blob. That's not a minus sign. So our values are minus 19, 101, and 20. Or sorry, at minus 20. So here is our max, and there is our min. So this is a pretty good problem because it combines together both 14.7 and 14.8. We use 14.7 to find critical points. We use the theorem at the end of 14.7 to guarantee that we'll find max and min here on our closed bound domain. And to optimize on the boundary, that's something we're going to do with Lagrange multipliers. So a very typical problem. Good one to bring together a lot of things here. Okay, let's look at our next problem. Look at problem number 19 here. Find max and min values of this function subject to that constraint. So f of xy is going to equal x squared y plus x plus y, and g of xy is equal to xy is equal to 4. So we're going to max and minimize this subject to this constraint. So it looks like we should use Lagrange multipliers. So let's go ahead and use Lagrange multipliers here and see what happens. So gradient f is equal to lambda times the gradient of g. The gradient of f is going to be 2xy plus 1. And the gradient, I should keep going here, and x squared plus 1. And the gradient of g here, so the partial derivative of this respect to x is y, and the partial derivative of this respect to y is x. So we've got our equations here, 2xy plus 1 is equal to lambda times y, x squared plus 1 is equal to lambda times x. Let's make these two look like each other. Let's multiply that by x. Let's multiply that by y. Multiplied by y. Multiplied by x. And so, what do we end up with? We end up with 2x squared y plus x is equal to x squared y plus y. So at this point then, we've got this equation to work with. It looks kind of messy, but let's use this fact here. This tells us if y is equal to 4 over x. So we can reduce this down to a function, an equation involving just one variable. So that would be 2x squared times what is y, 4 over x plus x, is equal to x squared times what is y, 4 over x, plus 4 over x. So simplifying the multiplication here, that is 8x plus x is equal to 4x plus 4 over x. So on the right here, 9x is equal to 4x plus 4 over x, or 5x is equal to 4 over x. Or cross-multiplying here, cross-multiplying gives us that x squared should equal 4/5. So x would be plus or minus the square root of 4/5. Let's go to a new slide here. X would be, if x is the square root of 4/5, y would be 4 over that. And if x is equal to minus square root of 4/5, y would equal negative that. However, as it turns out, so you might think that right now the approach is to take these points and plug it into our objective function. Pick the larger point to be our, pick the larger function value to be our max, pick the smaller function value to be our min. However, I think this was a WebAssign problem, and as it turns out, the answer is the max and min don't exist. I think many people were confused by this, so let me comment as to what's going on here. As it turns out, I worked through this, and I wanted to work through this as a good example of working through Lagrange multipliers. However, as it turns out, the different way to attack this, in which that lets us see that yes, there is no global max and min on this constraint, it's let's draw what this looks like. X times y is equal to 4. So x times y is equal to 4. So we have two different branches of a hyperbola here. Now, so what's going on? The points that we found, they're going to land right there. But however, so we might think local max and local min after plugging stuff in, but let's think about what are the limits as x goes to infinity here. So remember that we have y is equal to 4 over x. So if we substitute in y is equal to 4 over x into our objective function, we end up with f of x is x squared times 4 over x plus 4 over x. And that is 4x plus x plus 4 over x. That is 5x plus 4 over x. And the thing to realize is that the limit as x goes to infinity of f of x is just going to be, as x goes to infinity, this goes to infinity and that goes to 0, it's infinity. The limit as x goes to 0 from the right of f of x, going off this way, is also 0. That would go to 0 and that would go to positive infinity. If we took the limit as x goes to minus infinity of f of x, we get minus infinity, and this also gives us minus infinity. So here's a little sneaky thing. It's not really a Lagrange multipliers question, and the thing to realize here is that our constraint was not bounded, therefore we are not guaranteed to both have either a global min or a global max. In this case, we had neither. So this is a kind of tricky thing to watch out for as you tackle these kinds of problems.